So now it's time to try to draw a graph of this equation, y squared equals x cubed plus x squared. And I listed all the points that we found so far here on the side again. It started out as pretty smooth sailing, and then it kind of got crazier and crazier as we went along. Just if simplifying the radicals is hard for you, for much of the work that we do, if you left 2 square root of 3 as just square root of 12, it's not so bad. It's fine. Or square root of 2 over 4, if you left that as a square root of 1/8, it comes out the same. Again, the decimals come out the same. Now to plot these points, I'm seeing pretty small numbers and also a lot of decimal values. I got to try to get some of these fractional values on there. So I'm actually going to set up my scale where 2 squares is 1, 2, 3, and do that on both axes. So be aware that you can change the scale on the axes to fit the data you have or the values on the points. We just want to make sure they fit in okay. Okay, let's start plotting points. 0, 0. Negative 1, 0 is right here. Then I have 1 square root of 2, 1.41. So now there's a line at 1.5, so I'm just a little bit below that line. And also 1 negative 1.41, that's negative square root of 2. I have 2 square root of 3, but that's 3.46. So 3.46 is just below. That's going to be 4 up there, so 3.5. And here's negative 4. And then I have 2 negative that same value, so negative 1, negative 2, negative 3.46 is down here. And now our two mystery points, 2 ugly points, negative 1/2, 0.35. So let's see, negative 1/2 here. 0.35 is, so somewhere coming up that, not quite 0.5, right? So 0.35, I'm just going to estimate. And also negative 1/2, negative 0.5. So I just don't think it's obvious at all what the shape of this graph is. I have my pencil here, but I guess I kind of see something going on here. I kind of see something like that here. But what's going on in between, I don't know. And what I'm going to do is summon Desmos to help me out. So take a shot at it. Try to come up with something. And again, if you get it, great. If you don't worry about it. On my tablet here, by the way, I added the new equation to the old from the previous exercise, and so it drew both graphs together just for comparison. I'm going to blow this up a little bit with my fingers. And the blue graph is our new one. Let me get rid of the old for previous exercise. It's this funny kind of loop-de-loop. And maybe you had guessed that, but if you didn't, it's fine. This graph comes down like this, comes down to that point, curves around, comes back, does its loop-de-loop, and comes down below. So it's, again, nothing you would have to memorize or know. It's just an interesting example, and I did the exercise more for us to get the experience of solving some of these equations, plotting points. But this graph now that we see it does have a certain kind of symmetry, a different kind of symmetry. This graph has x-axis symmetry. And x-axis symmetry is the way, if you compare it to y-axis symmetry, it's like if we folded this graph on the x-axis, the two halves of the graph would match up, would come together. Here's another picture of another graph that has x-axis symmetry. It's different from the one we just did, but I drew it on larger paper so that we can see that when a graph has x-axis symmetry, If the point xy is on the graph, then the point x minus y is also on the graph. It's kind of interesting that it's the y-coordinate that changes with the x-axis symmetry. But if you look at this picture, you'll notice that the 2 points that would kind of fold together through the symmetry have the same x-coordinate but opposite y-coordinates. So it's really the change in the y from y to minus y that's a signal of this x-axis symmetry. And to test for it, what you can do is, because of this relationship between xy and x minus y, you can just check the equation by replacing y with minus y and seeing if an equivalent equation results. If that's true, then the graph must have x-axis symmetry. So in the future, we'll use this test more often with graphs we haven't even looked at yet. But let's go ahead and test this equation for x-axis symmetry. So I take the equation and I'm going to replace y with minus y. Minus y squared equals x cubed plus x squared. And then I'm going to simplify. I guess I'll go to the side here where I have some more room. Simplify. And for our examples, usually there will be something obvious you can do. And this is similar to the previous example where minus y squared, negative y times negative y, is the same as positive y squared. So we have the original equation. And so the graph does have x-axis symmetry, which we already know. Now, what we can do, since we have 2 symmetry tests, we're going to do exercise 5 before we finish this video. We can apply the y-axis symmetry test to this equation. Does this graph that we just did up above, does this loop-de-loop graph have y-axis symmetry? Well, we would replace x with minus x. In both instances, every place x occurs, it gets replaced with minus x. And then we have to see if an equivalent equation results. We have y squared equals, now, minus x cubed is like a negative times a negative times a negative. When that gets multiplied out, it will be minus x cubed. But minus x squared will just be plus x squared when it gets multiplied out. So notice this is not equivalent to the original equation. So the graph does not have y-axis symmetry. And we kind of knew that, right? Because we can see that when we fold this graph along the y-axis, that the portion of the graph to the right of the y-axis is very different from the portion of the graph to the left. This graph clearly has x-axis symmetry and no y-axis symmetry, which we just verified with exercise 4 and exercise 5. We'll continue the handout in the next video segment.